the string vibrates with a fundamental frequency. The fundamental frequency could be doubled by. We know that when the string is vibrating in fundamental frequency, there is a wave pattern like this. Wavelength lambda over 2. There is only one loop, then you have to get half of wavelength. It equals to length. Now lambda over 2 equals L. Lambda equals 2L. Wavelength is 2L. Now we can write V equals S lambda. We can use V equals S lambda for any type of wave. Then V is the velocity. Velocity of wave in a string, velocity of transverse wave in a string is tension over linear density square root of tension over linear density equals if lambda value is 2L. Now I will subject F 1 over 2L into square root of T over M. Now you have to consider the given answers. You have to consider given answers. The fundamental frequency could be doubled. First statement, halving the tension. We know that when tension is decreasing, frequency should be decreasing. Decrease because of there is a directly proportional relationship. Then it is false. Doubling the tension. We know that when tension is doubled, there is a square root, therefore frequency should be root 2 times of initial value. There is a square root. Then we can't get frequency doubled. Then third one, doubling the length. When increasing length, frequency is decreasing. Therefore it also false. Halving the length. Now we can get when length is half of initial length, frequency should be doubled. There is an inversely proportional relationship. Then answer is 4 for the two vibrating strings under the same tension would be produce beats if there are 3 statements A, B and C. The wavelength of their sound differ only slightly. We know that we can observe beats if there are 2 waves in a medium at the same time with a small difference of frequency. Then A is correct. If the wavelength is differ only slightly, we can observe frequency because of when change in frequency, we can change the when changing wavelength, we can observe that frequency is changing. Then it is correct. Then statement B, their length differ slightly, but linear densities are same. Yes, it also correct. Linear density means simple m value. If it is constant, they have given there is the same tension, therefore V is constant. V equals S lambda, then V is constant. If there is a different length, lambda is changing, then frequency is changing, then it is correct. See, their linear densities differ slightly but lengths are same. Yes, we can change the frequency. by change in linear density. All three statements are true. Then answer is 4. Consider the following statements made about transverse waves in a string. Statement A, they are associated with compression and rarefaction. No, we know that when considering transverse waves, we can't observe compressions and rarefactions. We can observe compressions and rarefactions for longitude waves. Then it is false. Then statement B, they are associated with strokes and crests. Yes, it is correct, because of it is a transverse wave. Then statement C, the shortest distance between two particles in the identical state of motion is one wavelength. Yes, it is correct. We know that distance between two successive identical phases, like this one and this one, there is the same motion, same velocity and same direction. Then it is the distance between 2 points is the wavelength. Then only B and C are true. 5 is the correct answer. A certain length of sonometer wire, when vibrated with another sonometer wire, produced 2 beats per second. In two separate instances, for the length of 122 centimeters and 120 centimeters, if the second sonometer wire, the tension of the second wire was same was both occasions, and they were made to vibrate the same overtone. The frequency of vibration of first wire is, they have given that there is the same overtone. If we are considering it as the fundamental, we know that lambda over 2, wavelength divided by 2 equals L. Therefore, wavelength is directly proportional to length. Wavelength directly proportional to length. Therefore, we can observe, we know that V, according to V equals F lambda, when velocity is increasing, frequency should be less than previous situation. When wavelength increases, frequency decreases. There is an inversely proportional relationship. Therefore, we can observe high frequency for the small wavelength, small length. It means 120 centimeters. Low frequency for the 122 centimeters. And they have given beat frequency is true for the both situations. It means difference of these two wires and these two wires are same. It is 2 Hertz. Difference is 2 Hertz. If the frequency of this wire is F1, we know that F1 is greater than F2. Then we can get frequency of this wire should be less than 2 Hertz because of beat frequency 2 Hertz. Then we can get F1 minus 2 is the frequency of this wire. We can get it is directly inversely proportional to length. Frequency of wire inversely proportional to length. I will derive it by using this equation. V equals F times lambda value is 2L. According to this equation, I have considered fundamental, but they have not given corresponding overtone number. But for the for any overtone number, we can get frequencies inversely proportional to length. Frequencies inversely proportional to length. Then frequency of this wire can be get as F2, F1 minus 2, because of there is a difference between these two wires. Difference is equal to the beat frequency. It is given as 2. Then it should be inversely proportional to length of this wire 120. I can get it as the first equation. Then for the second situation, we can get again difference is 2 Hertz, but now frequency of this wire is greater than this one. Then we can get F2 plus 2 is the frequency of this one. So I have considered length of this wire. Therefore, we have to get relationship for this frequency. If the frequency of this wire is F, we can write F1 equals F plus 2. Then frequency of this wire F plus 2. It is inversely proportional to 1 over length. Then for this wire, F2 should be equal to F minus 2. Difference should be 2 because of beat frequency is given as 2. Then F minus 2 inversely proportional to 1 over 122. Then it is the second equation. We can divide two equations. Then we can find the value of F. F plus 2 divided by F minus 2 equals 1 over 120 divided by 1 over 122. It means we can multiply by the reciprocal. Now we have to simplify it. We can use cross multiplication. 120 into F, 120F plus 120 into 2, 240 equals to F into 122, 122F minus 2 into 122, 244. Then you can find this value. 122F minus 120F equals 240 plus 244. 484 equals 2F. Then F value is 242 Hertz. Third one is the correct answer. Which of the following diagrams best represents the wave pattern at successions of time t of a stretched string fixed at both ends and vibrating at first overtone? The period of the vibration is equal to t. We have to consider shape of wave. When time is 0, wave form is this one. We know that when vibrating a loop with period t, if the first situation is like this, when completing full period, the waveform is again at this place. It means for the t over 4 times, it means 1/4 of period, the wave should be moved to this place. 1/4, half, 3 over 4 of period, full period. Then we can get, when getting second situation, wave should be like this. They have given this one as t equals 0, t equals t over 4. Then this point should be moved to this place and this point should be moved to this place. It means wave should be like this. After another t over 4, time is t over 2, then it is like this. Then the time is 3 over 4 times of period. 3 over 4 times of period. Again, wave should be like this. This point should move to this place and this point should move to this place. Now time is 3t over 4. When time is t, it means period. Again, the wave should be like this. Then we can get second answer is the correct answer. A violin string of length 0.4 meters is tuned to a fundamental frequency of 480 Hz. But by how much the string must be shortened to raise the fundamental frequency to 600 Hz. They have given the string is vibrating with fundamental frequency. Then waveform should be like this. Now we know that there is only one loop. One loop means wavelength divided by 2, lambda over 2, should be equal to length of the wire. Then lambda over 2 equals L, lambda equals 2L. Now we can use V equals F lambda. V equals S times lambda is 2L. Now we can use 2L because of they have given fundamental state. Then F equals V over 2L. V and 2 constant for the both situations. They have given frequency is changing by changing the length of the wire. Then frequency is inversely proportional to length. I will use this relationship for given two situations. In first situation, frequency is 480 Hz. It is inversely proportional to length of the wire. In first situation is given as 0.4 meters. For the second situation, frequency should be 600. I will consider new length of wire as L. Now there are two relationships we can divide. Then dividing, we can cancel out 0 and 0. 48 divided by 12, 4. 60 divided by 12, 5. 4 over 5 equals to 1 over 0.4 divided by this term. It means we have to multiply by reciprocal. Then we can find the L value. 4 into 0.4, 1.6 divided by 5. 1 divided by 5, 0. 16 divided by 5, 3. 1 remaining, 20 divided by 5, 1 remaining, 10 divided by 5, 2. 0.32 meters. Length for the initial situation, 0.4 meters. It means 40 centimeters. Now, new length is 32 centimeters. Therefore, change of length, decreasement of length should be 8 centimeters. Then we can get second one is the correct answer. Two steel violin strings A and B of the same length and subjected to the same tension have fundamental frequencies F1 and F2 respectively. The ratio of diameter of A divided by diameter of B is. Again we have to consider fundamental frequency. But they have given given two frequencies F1 and F2 and we have to get the relationship between diameter. Now I will use the V equals S lambda equation. For the fundamental frequency, we know that wavelength is 2L. We can substitute tension over linear density, square root of tension over linear density as the velocity of wave in the wire. And we know that this is the linear density. Linear density means mass divided by length. We can get mass density into velocity. Sorry, density into volume, dV. Density into volume. Volume is cross-sectional area into length divided by initial length. Length of the wire is L. Then we can cancel out L and L. Therefore, we can substitute area, cross-sectional area of the wire, phi d over 2 squared. D means diameter. I will consider density as rho. Now, we can substitute this part for the linear density. Then we can get tension over linear density is this one, rho phi d squared over 2 squared means 4 root should be equals to F into wavelength 2L. Now we can get relationship between frequency and density. Frequency is inversely proportional to square root of d squared. It means B. Frequency is inversely proportional to diameter. Now, they have asked the ratio between diameters. Then we can write F1 inversely proportional to density of A, F2 directly proportional, inversely proportional to density of B. Then we can divide the equation. F1 divided by F2 equals 1 over dA multiplied by reciprocal dB over 1. Then we can get dA over dB, F2 over F1. Then answer is 4 for the question. The velocity of transverse waves in a stretched string depends on, we know that velocity of transverse wave, square root of tension over linear density. Then first statement they have given frequency of vibration. No, it is depending only on source. Frequency is depending only on source. It is not velocity of wave is not depending on frequency. Then second one, wavelength. It is false. Third one, amplitude. We know that when amplitude is increasing, energy of wave increases, but velocity is not depending. Fourth one, tension in the string. Yes, when tension is increasing, velocity increases. Tension decreasing, velocity decreases. Therefore, fourth one is the correct answer. The frequency of fundamental note of a transverse wave, transverse vibration of a stretched wire 1 meter long is 320 Hz. The fundamental frequency of second wire of the same material of length 1 meter under the same tension but having diameter 4 times larger is. We can use same theory. Frequency inversely proportional to diameter. For the first situation, frequency 320, it is inversely proportional to diameter. For the second situation, diameter is 4 times, other all physical quantities are constant. We have to find the frequency. Then we can divide equation 320 divided by f equals to 1 over d divided by 4d. Then f should be 80 Hertz. Then answer is 1. A string is stretched between two fixed supports 0.5 meters apart and tension is adjusted until the fundamental frequency of the string is 440. The speed of the transverse wave along the string is. We can use V equals f lambda. We know that wavelength is 2 times of length for the fundamental frequency. We have to find V. Frequency is given as 440 into 2 times length. Length is 0.5. We can simplify it. 440 meters per second. Then answer is 4.